Welcome everyone. In this video we will solve yet another one of interesting physics Olympiad questions. Now this is again a Turkish physics Olympiad question to which you will be able to find the original paper in the descriptions part. Now here is the question. We have a surface which is pretty common for mechanics problems. And we have a loop. Interesting. And even more interestingly, we have a rod. We have a rod with mass M, capital M, and with mass, with length, capital L. It will be given an initial speed of V to the right. And it will travel through this loop, which has a radius of L. So the radius is the same with the length of the rod. We are told by the question that the hoop is frictionless and also the surface is frictionless. We neglect any frictional forces. We are given the moment of inertia of center of mass with respect to, so we are given the moment of inertia with respect to the center of mass of the rod, which is 1/12 ml squared. Now, we're asked to find the minimum speed, minimum V required, so that the rod will be able to make it through the loop without falling. How do we approach this problem? Well, to first approach, we need actually two ideas. Idea number one is considering the forces, and idea number two is considering the conservation of energy. And why is energy conserved? Well, because we assume that any frictional forces are negligible. And actually, I just realized, before we even come to those 2 points, we need to take a reference point. We need to say, if the rod will make it through the loop without falling, there is a critical point which we can point out and say, alright, if the rod passes through this point, it will pass through all the points. So there should be a point of interest, which is the most difficult, let's say, point to pass. And that point is, of course, the top point. When the rod is at the top of the loop, it is closest to fall. So if we write a condition, let's say, for the top, and if that condition satisfies not falling, then all the other points satisfy it as well, so the rod makes it through without falling. Now let's start then. At the top, what are the forces? We have this rod at the top. It will be pushed by the rod, and the push will be downward on each side, so it is like this, and N, okay, and N. There is the mass of the rod, of course, which is mg, and since this is a uniform rod, I didn't say it perhaps, but it is a uniform rod, the mg acts directly from the geometric center of the shape. Now, with this idea, we can write the force equation then. We will say, and I'm taking downwards as the positive direction for this force calculation, we can say that mg plus 2n is equal to the net force, which is in this case going to be, at the top, it is going to be mv squared over r. And v squared here is the speed at the top. Let's call it vt squared over r. This is the centripetal acceleration. We multiply it by mass to get the centripetal force. And notice that I didn't write L for R. There is a very important reason for it, which we will discuss in a couple of minutes, hopefully. Here, what is our condition? We will say for minimum V, we want the rod to be just about to fall when it reaches the top point. And what does just about to fall mean? It means that the rod is about to lose contact with the rod. So, the normal force is tending towards zero. Hence, we can say that this goes to 0 in the limit if we are calculating the minimum initial speed. In that case, we can also simplify by m to get that the speed squared at the top will be equal to g times the radius of the motion. Now here comes the discussion part. What is this radius? And as I said, it is not L. Because when we say radius, we in fact mean the distance between the center of mass of the rod and the center of rotation. So we are talking about this distance when we say r. And to be able to calculate that distance, we will assume that this rod has a very little height. So this height is actually exaggerated. It is much smaller. It is much smaller such that we can act as if, and let me even redraw it so that it is not confusing for you. This is a rod with a little height. So maybe something like this. So that we can assume the center of mass to be right at that point. And why is that helpful? Well, it is helpful because this will be L, right? I'm assuming, as I said, that this is a very small, this is a rod with a very little height, okay? This is an approximation. But what is not an approximation? I mean, come on. We neglected frictional forces, okay? So this is L as well. Due to our approximation, this is R. Now, we have that this length is also L, so we in fact have a triangle with 3 equal sides, an equilateral triangle, which means that this angle is 60 degrees. This is 90 degrees, so this angle is 30 degrees, which means that we have a shape that looks like this. A half triangle, one of the triangles is, this is R, this is L, this is 30. So, I see that R is equal to L cosine of 30, which you can recall means L square root of 3 over 2. So I am substituting that for R. G, L, the square root of 3 over 2. Cool. Now, as we said at the beginning of the video, we want to consider the energy. We said that the energy will be conserved. Let's say that the zero height is this point, just through the center of mass, and since the height of the rod is small, the center of mass level is the basically the level of the surface. Okay, the rod is barely above the surface, you can say. The top of the rod is barely above the surface. So it is 0, which means that the only energy present at the initial moment is the kinetic energy, which is 1 over 2 mv squared. This is going to be equal to, at the top, what do we have? We of course have gravitational potential energy. It will be mg, let me change the color, it will be mg times the height difference. What is the height difference? It is not 2L, be careful, it is L plus R. What is R? R is here, so it is L square root of 3 over 2. Plus, there will be a kinetic energy, of course, which is 1 over 2 v top squared. And what is v top squared? It is gr, which is gl times the square root of 3 over 2. So I am writing that. It is gl square root of 3 over 2 plus... Now, you might say, this is it. Why do you say plus? But in fact, there is one more term left. Because this is only the translational kinetic energy part. But since the center of mass is rotating around the center of the loop, we also need to add a rotational kinetic energy, which is in the form 1 over 2 I center of mass omega squared. I center of mass is given to us at the beginning. And what is omega squared? Well, it is simply, let me write it at the top left. Omega is V over R. More specifically, the speed of the center of mass. So let me just substitute all the values step by step. We will have I center of mass. We have, alright, so we have 1 over 2. I center of mass, this quantity, which is 1 over 12 ml squared, times we have the center of mass, we had omega squared, so we will square this part. We have omega squared, v center of mass squared, r squared. What is v center of mass squared? It is going to be the speed at the top squared, this part. It is gl square root of 3 over 2. And then we have the, oh, we don't have enough space though. Let me make it a little smaller. Okay. And then we will have a division by r squared. What is r? It is L times the square root of 3 over 2, which means if we square it in the denominator, please check my math, it will give us, let's see, L squared, and then a 3, and then a 4. Okay, as I said, please pause the video and make sure that this makes absolute sense to you. Here, we now can cancel the masses. Chat, 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 chat. They are gone. And I want to have this L multiplied by 2. So we have 2L plus L times the square root of 3 under the same denominator of 2. And you might be saying, why did you do that? I did that because I can simplify by 1 over 2 now. This guy is gone, that guy is gone, this is gone, and that is also gone. Which leaves us, my friends, with the equation that v squared is equal to. Let's see, we will have g, let's factor out L, 2 plus the square root of 3, alright, plus the square root of 3 over 2. And what else? Well, in the last term, you can notice that L squared cancels. This 4 and this 12. Well, that gives a 3. So what do we have? We have, let's see, square root of 3 plus the square root of 3 over 3 times 3 is 9 divided by 18. Interesting. Alright, so with this, we can now combine them under one common denominator, I guess. So this is going to be 9, 18 over 18, which gives you GL 2 plus, let's add them. We will have 18 plus 9, which is 27, plus 1, which is 28, square root of 3 over 18, which will, of course, simplify to GL 2 plus 14 square root of 3 over 9. And this is the formula for V squared. We want V, so we take the square root and say that V, the minimum initial speed required for the rod to make it through the loop without falling, is equal to the square root of GL times 2 plus 14 square root of 3 over 9. Anyways, I hope this video was helpful. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.